One sec here. Okay, here we go. I'd like to move on to stress distribution in soils. And hold on here, that guy disappeared on me. Please excuse the delay here. There we go. Now it's back in action. So I'd like to look at this stress distribution beneath loaded areas. And for our purpose, I mentioned a lot of this will be done below foundations. And we need an entry point here to recognize that these are highly idealized solutions. They're conducted using a semi-infinite half space. That's quite interesting concept. It's half of infinity, effectively. Infinity with a plane above it, so kind of like the Earth's surface for practical purposes. You know, it goes forever in one direction and starts somewhere. It is weightless. I haven't written that on this sheet, but the material at hand is elastic and weightless, so it's highly idealized, unlike real soil, which would not be elastic and certainly not be weightless either. We're going to use normalized geometry in all of these methods. And this is with respect to B, L, and Z. And in some cases, say for an embankment, we'll get into some other dimensions as well, but these are the big ones for foundations, in which you would speak of being, for example, at a depth 2 diameters below the foundation, or 2 dimensions B, 2 width dimensions B below the foundation. And we need to sort out the stress change at that location due to application of a load on that foundation base. And the normalized geometry will allow us to utilize charts or equations and arrive at an influence factor, I, and the change in stress that will result from applying a load at the surface is going to be the stress acting at the surface, the stress over that loaded area, times this influence factor. So this would be the stress acting on the base of the foundation for the case of a shallow foundation version. And we'll need to do a little bit of extra bookkeeping to make sure that the foundation base is represented mathematically as being, quote, at the surface. Something that I like to use for these, some of the charts and so on that you'll see today have this notation, which is delta sigma. That's a change in stress. And what that means is a change in stress due to application of the load at the surface. Some of the charts will show it simply as sigma. I like to show it as delta sigma just to remind us all that, this is an extra stress being applied, and there's the regular stress that exists due to soil weight already in place. So I have a packet that I've uploaded to Canvas for you, and I'd like to run through that. And before we jump there, I'll show a few images and then run through that entire packet as kind of a wrap-up. And I'd like to look at a starting point for these calculations. This is a graphic out of the Holtz and Kovacs textbook. And this is utilizing a very simple technique called the 2-to-1 method. And it's a broad approximation for what is happening with stress at depth from a stress being applied at the surface. So there'd be a stress acting on a foundation, the foundation shown here, B times L. And the stress acting is going to be load, P, divided by, in this case, it's a strip foundation on the left, and on the right, it's for a rectangle foundation. So on the left, it's B times 1, just taking one slice into the page. And what is assumed in this method is that we have a bridging of load to allow carrying that column load or that foundation load, whatever it is, by a broader amount of soil, a greater width of soil with depth. And that bridging would be occurring at approximately a 2-to-1 angle from the foundation pad, let's call it up here. And that same thing is occurring in 3 dimensions over here if we have a B and an L. So you would have the B dimension spreading out to account for a B plus Z, and where that's coming from is B originally, shoot it on down. And we have a depth Z of interest. So we're looking at what is the stress acting at some depth Z. Well, it'll be Z over 2 based on our slope, and that would be occurring on both sides. So you'd have Z over 2 and Z over 2. And therefore, the stress acting on this plane for a strip foundation is going to be Q naught times B times 1. That's the load that is acting up here. And what we're doing is dividing that load by a new area. And that will be B plus Z times 1. So B plus Z times 1 into the page is the new area of that foundation. Same thing over here. So we have our stress that's acting on the foundation, P over area, P over B times L. And we call that a starting stress, let's say, acting on the foundation. On that, over that area, it's acting over that area. And we would then divide by the new area. So what this is, something that is not cleanly shown in this, which I think is worth mentioning at least, is the fact that the stress acting at the surface is going to be load over area. That shouldn't be a big surprise at this stage, load over area. And the stress acting at depth is that same load over a new area. And Holtz, Kovacs, Sheehan have gotten into this, calculating out as a stress acting on the surface. And that's great when you have a stress acting on the surface over a given footprint. But if you simply have a load acting, you can do this without even calculating that Q naught term. You can just grab it directly as being load over new area. It's a bigger area down here. This large rectangle is B plus Z times L plus Z, applying the same logic as we had over here, where it goes Z over 2 in each direction. You have to recognize that's happening both into the page and sideways here. And that's your new area of your base down here at the bottom that would actually be supporting that load. So load over this bigger new area. And therefore, you would expect that it will be a lesser stress at depth. That is hopefully quite intuitive that you would have something like that going on. I spoke of a normalized approach, normalized dimension. And this is called an M. I'll just refer to this as an M and N chart. M and N. I'll make this full screen. I presume that's still showing. I changed a presentation mode so you see it a little larger. So this will be called the M and N chart. And what we're going to do here is define M as being X over Z. For our purposes, we could say B over Z. And N is Y over Z or L over Z. And as it turns out, M and N are interchangeable. If you have a graphic like this that is properly typeset, it will work. Mathematically, it works out absolutely that they are interchangeable. I have seen some versions in print where it doesn't quite work, just in how it was printed or something little like that. But in this, you have a sigma at depth. Oh, I'm sorry. A sigma at depth, what I've called delta sigma, is equal to the stress acting at the surface on that area, on that shaded area, times influence factor. And how do we get at an influence factor? We need to arrive at some point within this graphic. And I'll give you a little bit of bearings here. M is this family of curves. So 0.1, 0.2, 0.3, 0.4, 0.5, and so on, all the way up here to infinity. So you simply interpolate. You're interpolating between 0.5 and 0.6. You're interpolating up here between 3 and infinity. And you see that they collapse quite a bit there, so it's not problematic to do so. And N is down on this side. On this axis, the x-axis is N, and something to note, this is a log axis, so you got to be careful with which set you're in and so on. And here you would identify the value for N, again, defined as L over Z, so quite straightforward. And you end up at a given point here. And once you reach, let's say you're at 0.55 and 0.8, you'd be somewhere around here for a data point, and you'd shoot over them and get an influence factor of 0.15 or something like that if you were residing right here. Less than 0.12, interpolating up to that 0.12. And then you'd be able to sort out the stress at that depth of interest. And again, it will show up that for deep points, you will have less stress acting in that regard. This is a version for circular loaded areas. So it's identical kind of solution. in terms of having an influence factor result. In this case, the influence factor is across the top. And the two values here are going to be x over r for an offset. Those are in circles. And z over r, the depth identified in radii shown here. So this works identically to that and allows you actually to get outside of the footprint of that circular loaded area. This would be a classic application for, say, a petroleum storage tank, in which you have a cylindrical tank that's loaded, a good portion of the year, and you need to sort out what settlement will be occurring, and do you have a forgiving enough membrane at the base of that tank to allow for appropriate service in that environment, sort of thing. But the idea would be the same, that you'll end up at a given point here by interpolating both the depth and radius, and on the family of curves, the offset over the radius. And when you identify that you're at a point, you shoot up and you'll get an influence factor. This time, influence factors on a log scale, by the way. So you're going from 0.1 all the way over here up to 80 and 100 on the right side. And finally, we have a version in which there is an embankment presented. And the embankment is probably the most challenging of the shapes. And does utilize normalized dimensions A and B, the horizontal projected distances of the top bench of the embankment and the slope of the embankment. And all of this, you have to recognize, is for a half of an embankment. So this would behave right here as a center line for this embankment. And there'd be a mirror image of it over on the right side that would relay as well. And we again go through an A over Z and a B over Z, B over Z being the family of curves this time, A over Z being the log scale x-axis. And then you'll arrive at an influence value on the y-axis this time. And you'll see that that influence value maxes out at 0.5. So if you have a huge embankment and you're right below the middle of it here, you're considering the left half of the embankment, you would have a 0.5. And what you would have to do is multiply that by 2, because there's another half of an embankment that is present in real space that you'd be accounting for. And that would bring you then to an influence value of 1, more or less treating the embankment like a layer of soil, which is not unrealistic for shallow depths, given dimensions of embankments and so on. I'd like to look at an example problem here. And let's determine the delta sigma beneath the corner and beneath the center of a 3 by 4 meter loaded area at a depth 2 meter below load application elevation. And the load is going to be 6,000 kilonewtons in this case. And for a corner type location, we'll be using the M and N chart in both cases here. We will have M is B over Z, as I mentioned, or X over Z, if you're following terminology in that slide that was just shown. That'd be 3 over 2, 1.5. N is L over Z, or 4 over 2, having a value of 2. And you can run to the M and N chart looking something like this that has been posted on Canvas for you. It's a packet with numerous handouts in it. I think this is the first page. And we are looking for a 1.5 and a 2. So we have a 1.5 would be right between here, and the 2 would be coming down from here. And we interpolate to the 1.5 right about there. So what influence factor do we have here? If we shoot over, the influence value is going to be what? Right about there. 0.222, something like that. Are you seeing where that's coming from? We're between 1.5, 1.4, and 1.6. Our value is 1.5. So we're right between these two curves, and we follow it in a curvilinear fashion. So we're interpolating between those two, and just by observation is plenty of resolution for us. Remember, this is geotech. And 2. So we're coming right in on that line. So that line and right between these two is where we're at. I'll call it 0.222 for this, and 0.223 I actually had done for this calculation, but you're in that, certainly in that ballpark. We're out to a third dimension here. I'd feel comfortable having, a little bit of play in that third decimal. So the Q naught, this would be acting at the surface, is going to be the load acting at the surface divided by the area of that foundation. So 6,000 divided by 3 times 4, 500 kPa. And therefore, the change in stress at this depth of interest, which is 2 meters below the corner, is going to be 500 kPa times 0.223, or 111.5. Are there questions on determining the stress beneath the corner of a loaded area using that M&N chart?
So when you're saying corner, are you just talking about just a quarter of the foundation, or like the very corner of the foundation itself?
The very corner of the foundation looking down in plan view. So if we go back here, it would be this point right here. Any one of these 4.
Okay.
Any one of the corners, the 4 corners. They'd all be the same, as it turns out, due to symmetry. But you'd be picking one of these. That making sense? How we arrive at that? So that's a direct use of the M&N chart. And it's just drops in your lap. It's exactly what the chart is designed for, and it allows for application of that quite a straightforward manner. There's a center portion of this question, though, also of interest. I'll back up now. Is what is the stress 2 meters below the center of the foundation? That'd be a concentric point, typically where the column would be on a foundation. So now we're down here, 2 meters below that is where we are in the problem, and right below the center of the foundation. Well, it's hugely important when you use these types of graphics. They're wonderful graphics. This is out of the Navy Facility Command Design Manual, the NAVFAC DM7 set, which I mentioned on day 1 of the class, being a fantastic resource for you. I'm providing what you'll need in the course from that, but it is just a good PDF to grab for your files. These are wonderful graphics. This is one example of a kind of, a page from that document where it's literally one-stop shopping. It describes everything you need. You can use this without any training. You just jump in. It has everything you need defined for you and, ready to go. And now we're trying to get to the center. But back to the importance of, it is important that you read the captions and the footnotes and things like that in these tables, and you adhere to it, or else you're not using it properly. And this table specifically, this chart, I should say, is used to obtain the stress beneath the corner of a rectangularly loaded area. And as long as you're using it for that, you're fine, but you do not want to deviate from that intended use. And now we're being asked to determine the stress beneath the center of the foundation or this loaded area using the same chart, as it turns out. Well, we can be creative in our use of the chart and do something like this, where we hatch out 4 little rectangles. And since it's right in the middle, it would be symmetrical, and we can determine the M and N for one of them, determine the contribution of stress change due to that red shaded area. And at the end, we're going to multiply it by 4 to account for 4 little chunks. And these don't need to be all the same. You can get into having different areas in which you're actually summing it, as I'm showing over here in the math as the problem unfolds. We'll get to that in just a sec. But the idea here would be M is X over Z, or B over Z as we've called it. Now we're talking a half a dimension here. The red square is what red rectangle, is what we're quantifying here. So 1.5 over 2, we're still interested in 2 meter depth, and that's 0.75. N is L over Z, and that would be 2 over 2. Again, half the dimension here of the side, and that's going to be 1. You can utilize that M and N chart, and you'll see that it's on the order of 0.157. I'll let you look at that on your own. Q naught is still 500 kPa. That has not changed. It's still 6,000 over 3 times 4. That is the stress acting at the surface, after all, on that loaded area. And that's an important point here. That hasn't changed. We're not changing the area and saying all of the load is being applied here. We're just saying this is a piece of loaded area of smaller dimension, but each of these will be loaded by that same 500 kPa. And the delta sigma that we have is Q times I. In this case, it's times a summation of I. So you'd have contribution of square 1, contribution of rectangle 2, contribution of rectangle 3, contribution of rectangle 4. And if they happen to be different sizes, you can actually manage that, go to the chart 4 different times, obtain M and N each time as needed to get appropriate values. And that will be 500 kPa times 4, that's taking care of the summation, times 0.157, our influence factor that would come from the 0.75 and 1 values for M and N respectively. And we end up with 314 kPa. Is that higher or lower than at the corner?
Higher.
Higher. And does that make sense that you're going to have a higher stress beneath the center than you would under the corner?
I guess so.
All righty. With great confidence, Kurt rings in, and absolutely true. That is the case. It will be a higher load felt beneath the center of a loaded area. And that would be, for instance, why when you're setting a ladder, up and you're going to climb on it and so on, you want to be careful about where those pads are, and you want the centers nicely supported and so on, as they are holding a good majority of the loading. So that sort of logic would apply. And similarly, you can get into extensions on this problem, and I'll show you a few examples of that. I alluded to at least one. in this case, if we're looking down in plan view, and you would be interested in what is the stress distribution or what is the stress change beneath at that point, it would be a matter of a similar kind of logic. In which you would identify 4 zones now, 1, 2, 3, 4, and be able to enter the M&N chart each time and get the influence of each of those shapes and then sum them at the end. So it's handy for rectangular foundations outright. You do not need to be at the corner. You need to be at the corner to be using it, but you can be clever and oversee that chart and actually use it beyond its intended mean to some degree.
And then we would just add all of the I's together, right? Like we did.
That is correct. It'd be a summation of the I values, correct. Absolutely. How about that one? What if you're interested in getting a stress change below a point that's outside of the foundation with the condition of trying to be at the corner to utilize the chart, if we're using the M&N chart to do this? Any thoughts on that one? Is it possible to do that? Can we use the M&N chart to get stress at that location?
Would you split it up like how you did for the other one that was off center, and then like use triangles to figure out at what depth it would hit the corners of those split up rectangles?
You're on a path that shows some promise, but not quite there, Lauren. You're getting at something with like the method before. What did we do before? What was this process? What did that involve? We weren't utilizing the entire foundation. We were building what we could consider some virtual foundations just for the convenience of using the chart. Does that concept play out here? Do you think we could do that in this domain to force that point to be at the corner of a loaded area? Whoa. Any thoughts on that one? How about if we extend the foundation like that? And now we would be at the corner of a loaded area. The key here is that to do this, we would have to load that entire area. And we're not quite where we want to be with the problem, because now we've loaded the whole area and that's not actually what's happening. So can you see anyone see a solution to that, of how mathematically we can get out of this? We're on the right path here, but not quite there. Anyone see a method to, in a sense, undo that? What we went beyond the boundary? go back to this slide and show that the method when you're making virtual little pieces of foundations, you're taking a summation of I. And there's no rule that says I has to be positive. So given that, does that provide any incentive here for a different approach?
Can you find one I for the extended foundation and then subtract the piece that you extended?
That is correct. And what would that subtracted piece look like in this case? That's absolutely it, by the way. What did we add that was, call it, too much? It was out here, right? Almost a square out here. And I'll show this one with red shading going the other way. So for I, you would take this hatch mark and call it positive. And for I, you would take that and call it negative. And each time, we would be interested in what's going on at that point. So each time that we enter the table, I'll come back to this slide in just a minute. Each time that we enter the M&N chart, we would be in fact adhering to the rules for using this chart. We are determining the vertical stress under the corner of a uniformly loaded rectangular area. So we're fine. We can charge on and use the chart in that manner. And it's a matter of simply having that subtracted off. What if we had a situation like that? Similar method, right? We can extend out to include that. Like that. We'd have that. We'd go in and get an I value, M and B over Z, L over Z for this big shape. Excuse me. B over Z, L over Z for this big shape. And we'd grab an I value, and that would be considered a positive. And what do we need to do now in order to reflect more of a reality-based system? We need to get rid of some portion that isn't actually loaded in reality. And what is that?
Would it be this whole section here.
It would. Hey, pretty nice, Evan. I haven't seen that feature used. Cool. That would be it. And how are we going to divvy that up into pieces that represent rectangles with the corner being our corner of interest?
I think you need to subtract. Yeah.
This. And subtract that out. Okay. And then what else do we have to do?
Well, if you subtract this rectangle as well, then that gets rid of the other portion, but then you've subtracted the same area twice.
Okay, well, let's give it a shot. We can take this one out, is what I think I'm hearing, right? So now we got a real long one with vertical lines on it. That's negative. However, there's this area down here which is problematic in that it's been subtracted twice. We have to add that one back in because we took it out one too many times. Oh, sorry, here, missing out on the drawing. Looks like that. So you'd have the big green area, the whole thing. Go to the table, you're at the corner of a rectangle loaded area, check, it's a valid use of the table. Next up, you remove this vertical rectangle. You're fine. Using the chart, you're at the corner of a loaded rectangular loaded area. That's minus because you're taking that area out. Similarly, the long, shallow rectangle with vertical stripes on it is going to be minus. Now, though, this yellow area you've taken out twice, you actually have to add that in. And each of the 4 times that you'd be entering that table, you would be using it in a valid way. That's one check that's needed. The second check that's needed is that at the end, your loaded area represents what you thought it did at the onset or what it does in reality, and you're not just patching together, taking away things too many times or something like that. Are there questions on this methodology? This is, called superposition of these methods, and it allows you, as we see here, to work in both positive and negative notation for use of that addition of stress, addition or subtraction of stress. And therefore, with the M and N chart alone, you have a great power to establish what is the stress change anywhere under a rectangularly loaded foundation. So it's a highly capable methodology if you take it to its limit and utilize it in this fashion. I will hold off there for today and call it a lecture and look forward to seeing you folks on Wednesday for the midterm exam. So we'll see you then.